Now we look at some examples of applications of Taylor polynomials. So we first saw how to find a Taylor series for a given function and how to prove that actually the Taylor series is converging to the function. Now we see some applications for the Taylor series. So basically, instead of using a function, we use an approximation that we get from the Taylor polynomials. Just a short reminder of some of the series we already have that we need to remember because they are very useful. So the geometric series from the beginning, from which we can get many other series like the one here, and then if we integrate we get the series for ln 1 plus x. So basically we have one series, geometric series here, from which we can generate many others. And then also we have 1 over 1 plus x squared that we get from this series here. And obviously if we integrate this series, we'll get series for tan inverse. It is important to be able to recover those series quite quickly. So the most fundamental one is the geometric series here, and then just by replacing x by different expressions and integrating, we can get many other series. It's also important to realize what is the interval of convergence. This is another table of series, Taylor series. Most of them are actually Maclaurin series centered at 0. So these are the most frequently used ones, so it's important to maybe remember them. It's going to be faster to solve some problems if you remember these series. Just a reminder again regarding the way to generate or create a Taylor series given a function f. So this is a formula by which we create a Taylor series using a function f and Taylor series centered at number c. So the derivatives are evaluated at c, and then we have x minus c here. If the center of the series c is equal to 0, then we have a special name, it's Maclaurin series. We saw that before, and these Maclaurin series, they occur very often. Now, if we stop a series at some point, we get a polynomial, right? So the polynomial of degree n is called Taylor polynomial here, centered at c. So all we do is just stop a series at some point. So here at the polynomial of degree n. So this series centered at c, number c. So that's why we have x minus c, and it stops at the power n. So this is a Taylor polynomial of degree n. So now what we are going to do is, in general, we are going to use this polynomial to approximate the function f. Previously, we also saw that the function f is a sum of the Taylor series if and only if f is actually a limit of Taylor polynomials. And then we saw that actually if we just split it in two pieces, we have polynomial of degree n and then the remainder of the series. So the remainder is this expression here. So previously we saw how to find a way to have an upper bound on the remainder, so that will be a result that we will use. And we also saw that when the remainder goes to 0, obviously then limit of Pn is equal to f. That means that the Taylor series is converging to the function f that was used to generate the Taylor series. So that was the result we saw previously. Here is a reminder for the expression of the remainder. It's just an expression, so we have polynomial of degree n and then the remainder for that, so the rest of the series, and that remainder is equal to this expression. This is the result that we need for later on. Another version that is maybe more convenient and that we are going to use more often is this one called Taylor inequality. So if we can find an upper bound for the derivatives on certain interval centered at C, obviously, then we have the following result. The absolute value of the remainder is smaller than this expression here. So m is a number that we will find, so that will be a work that we need to perform, number that is greater than the derivatives at certain interval here centered at C. So this expression we need to remember it because we are going to use it in order to find the upper bound for the error. So when we are asked what is the error if we approximate sine x by a polynomial, Taylor polynomial of degree 3, well, we will find the error using this expression. And the result that we saw previously was that whenever we can find an upper bound for the derivatives on certain interval, then the remainder actually is going to 0, and that means that the function f that was used to generate the Taylor series is actually equal to the sum of the Taylor series. So that was a useful result that we saw previously. Knowing that, that means that our series is used to approximate f, so we use the polynomial degree n as an approximation for the entire function. So if we take function, for instance, cosine x, we can use a polynomial of degree 7, for instance, or 10, doesn't matter, as an approximation for the entire function. So the idea from now on will be to approximate the function f by a Taylor polynomial of certain degree n here, and then estimate eventually the error using the Taylor inequality. One of the observations is that the function f and the Taylor polynomial are equal at the center of the series, where we develop the series. Obviously, if we put x equals c, all of these terms here are 0, we are left with f of c and Pn of c, so obviously they are equal. So whenever we evaluate the polynomial at the center of the series, well, it's equal to the function at the center of the series. That's also true for all the derivatives, all the n derivatives of the polynomial. This is just an observation, nothing special about it. It's just an observation that the function and the derivatives are equal to the function itself. So the function and the polynomial are equal at the center of the series. So that's just an observation, nothing special there. To estimate the error, this is the result that we will need to remember, and we will use it regularly. So if I have a function f and I created a Taylor series, and then we prove that actually the Taylor series is equal to the function, I can use a Taylor polynomial of certain degree 1, 2, 3, 4, 5, 10, doesn't matter. So the Taylor polynomial is an approximation to the function. That's great. And now we need to estimate the error associated with that approximation. For that we use the famous Taylor's inequality, where the remainder, so the error, is smaller than this expression that we saw previously, where m is an upper bound on the derivatives on certain interval. So normally we are given an interval on which to work. So on that interval we need to find an upper bound for the derivatives. Once we do that, we have an upper bound for the error. So that's very important. So this part here needs to be memorized. And you see the polynomial degree n. Here we have n plus 1, n plus 1. So if I use polynomial degree 5 to approximate the function, so the error will be estimated by here 6 factorial and then here to power 6, right? If n is 5, So this is something important to memorize and to use whenever we need to estimate the error. There is an alternative when we have alternating series. So the Taylor's inequality is useful always, and we can always use it. There is no exceptions for that. However, when we have an alternating series, we can also use alternating series estimation theorem, which basically says when we have an alternating series, estimation of the error is given by the absolute value of the first neglected term in the series. So if we cut the series with a polynomial degree 5, well, the next term, so with the powers of 6, that term will be an approximation for the error. So that's valid only for the alternating series. But the Taylor inequalities is valid all the time. So even when we have an alternating series, we can still use the Taylor's inequality. There is no problem with that. But sometimes it might happen that the alternating series is present, so maybe it's easier for some people to just take the next term and use it as the estimate of the error. So it's totally your choice. Do you use the Taylor inequality, or you use the alternating series estimation theorem whenever you have an alternating series? It's up to you, but normally we use most of the time the Taylor's inequality because it's general and applies to all of our approximations. So regardless of the type of the series, Taylor inequality applies all the time. Here's an illustration just to see a little bit what happens exactly here. So if we take a function exponential x and we take a couple of Taylor polynomials that we produced just to see how it looks graphically. So we expand the exponential x around 0, so basically we are centered at 0, so it's Maclaurin series. So polynomial of degree 1 is 1 plus x, so that's actually the tangent line to the function exponential x at the point 0, 1. And then if we take a polynomial of degree 2, so we have another approximation, polynomial of degree 2. If we take polynomial of degree 3, normally approximation is better. So higher the degree of the Taylor polynomial, better the approximation. And that's what we see as illustration here on this graph. And you see the quality of approximation increases with the degree of the polynomial. So higher the degree, larger the interval on which the approximation is good. Obviously, let's say for the polynomial of degree 3, we see that if we move away from the center of the series here 0, if we move away from 0, the quality of approximation deteriorates. It's not as good as when we are close to 0. So that's why either we need to keep increasing the degree of the Taylor polynomial to improve the approximation, or, which is much wiser actually, another option, wiser option, is to expand the series, to create a series centered somewhere else. So depending on the area where we need an approximation for our function, that's where we should actually expand the series. We will see an example for that also. Here is the illustration that exactly shows that. So we use Maclaurin series, which means the series that is expanded at x equals 0. And here is an illustration. If we try to approximate the function exponential x at point x equals 0.2, so we expanded the exponential x at 0, so we got the Maclaurin series. And now we would like to know what is the value of e of x, where x is 0.2. So what's the value of exponential 0.2? With the calculator we can get the value that is quite good. Now what happens with the approximations actually when we use Taylor polynomials? So Taylor polynomial of degree 2 gives us a decent approximation. So we have already the 2 digits behind 2 decimal places already, just with polynomial degree 2, because we are very close to the center of the series. Center of the series was 0, so when we are close to 0, we get decent approximation. Higher the degree of polynomial, better approximation. And we see that very quickly, well, at polynomial degree 6, we are already getting a lot of decimal places that are correct. So whenever we are close to the center of the series, approximation is quite good and quite quickly. So we don't need to go up in the degree of the polynomials to get a decent approximation. We can use polynomials with quite low degree. Now, if we use the same Maclaurin expansion, so the polynomials obtained from the series centered at 0, but we want to know what is the approximation at x equal 3. So what is the value of e to power 3? From the calculator we get this. Now let's compare the exact value with the approximations. So if we use the Taylor polynomial degree 2 that we obtained by centering the series at 0, you see the approximation is 8.5, which is extremely far away from 20. So it's a horrible approximation, because 3 is very far away from 0. Exponential is increasing very quickly, so we have a huge error. So our series was developed at 0, and we would like to have an approximation at 3, so that distance is huge for exponential, and we have horrible approximation. If we improve the approximation, we need to increase the degree of the polynomial. So if we use polynomial degree 4 as approximation, we get something better, but it's still very, very far away. This is terribly bad approximation. And then polynomial degree 6, it's a little bit better, but still far away. And then 8 and 10. So basically we need to go to the polynomial degree 10 to get something decent as approximation. Whereas if we are close to the center of the series, very quickly we get a very good approximation. When we are far away from the center of the series, we need to go high in the degrees of polynomial in order to hope to get a decent approximation. So you see why, if we need an approximation around 3, it's better to expand exponential centered at 3, so we get a different Taylor series from the Maclaurin series, and then that one will give a better approximation in the neighborhood of 3. Maclaurin series centered at 0 gives good approximation in the neighborhood of 0, so we see that, but it's a terrible approximation far away. So that's why we sometimes need to develop or expand our Taylor series at different points in order to have a decent approximation very quickly with lower degree polynomials, because computing the value of these polynomials has a cost. Higher the degree of the polynomial, more terms you need to compute. Here is an illustration how to use the Taylor polynomials and how to estimate the error. So let's say we have a function which is third root of x, and we are asked to produce Taylor polynomial of degree 2 centered at 8. And then once we have that, we need to compute the accuracy of the approximation of Taylor polynomial of degree 2 in the interval 7, 9. So that's the task here. So first thing, we need to find the polynomial, Taylor polynomial of degree 2 centered at 8, and then second step will be to find the estimate of the error in the interval 7, 9. So how do we find the Taylor polynomial? Well, it's not complicated. We start like we did to compute the Taylor series. So we have our function, and then we compute the derivatives. Now here the degree of the polynomial is 2, so we need to compute the second derivative, which will be used to generate the polynomial. And then the error term, we know we need the next derivative, so that's why we have the third derivative computed also. And then the series is centered at 8, so we need to evaluate function and the derivatives at 8. So these are the values. So now we are going to use this in our formula for the Taylor polynomial of degree 2. So simply we stop our Taylor series at polynomial degree 2. So that's our approximation. So we have the coefficients that were computed here, 2, 1 over 12, negative 144. So we plug them here into the formula and we get the expression for the Taylor polynomial of degree 2 centered at 8. So the approximation with the second degree Taylor polynomial centered at 8 of the function third root of x is given here. So it's just simple computation. Now the next problem is to find the estimate of the error. So one of the tempting things is to say, oh, but this is an alternating series. Well, not really. It is alternating when x is bigger than 8. But if x is smaller than 8, both of these terms are negative, so it's not actually alternating. So this means that we cannot use the alternating series estimate theorem, which is not a big deal. We always use Taylor's inequality. This is just to make sure that you don't misapply the alternating series theorem, because the polynomial here, the part of the series that we have, is not actually alternating. It's not alternating on the interval that is given to us, 7, 9. So we absolutely have to use the Taylor's inequality in this case. So our polynomials of degree 2, so the next term in the error is with n plus 1, so with 3, and it's centered at 8. So this is by the Taylor's inequality, the formula. In this case, we need to find the m, which is an upper bound for the third derivative. That's by the result, which is Taylor's inequality. So we need to find a number m that is bigger than the third derivative of the function on the interval 7, 9. So x varies between 7 and 9. So we need to find a way. So what's the third derivative? Well, it was already computed here. The third derivative is given here. We computed it. So now we need to take absolute value and then find m such that m is bigger than absolute value of the third derivative on the interval 7, 9. So this is the procedures. Essentially, we realize, okay, x is between 7 and 9, so we have this inequality because we need to use 1 over, right? So that's what we have here, because the formula is given. It's 10 over 27, and this is the negative power, so it's 1 over x 8 over 3. So we basically need to find an upper bound for the third derivative on the interval 7, 9, because that was given in the question, interval 7, 9. So here is a number. So if we use this number as m, we are good to go. We have that the third derivative is smaller than this number here. So that's all the work that is required here. Obviously, if x is between 7 and 9, x minus 8 is smaller than 1. So that's obvious, because in the question it was given that x is between 7 and 9. So in that case, our remainder is smaller than this expression here, which is smaller than 0.0004. So on the interval 7, 9, the approximation is accurate to this precision here. So our polynomial of degree 2 on the interval 7, 9 is accurate to this precision here. So that's what we got as a consequence of applying the Taylor's inequality to estimate the error. Now, another type of application is if we need to find an approximation of a function at certain point. So here, the task that we are given is to use Maclaurin series. So we expand sine x at 0. So center of the series will be 0 because we are asked to use Maclaurin series. And we need to use that Taylor expansion to find an approximation to sine of 1.234567. Obviously this is in radians, huh? And it needs to be accurate to 10 to power minus 11. So it's a huge task here. We need to find the huge accuracy. So since the goal is to use Maclaurin series, obviously that's not the best option, but that was the question. We need to expand our Taylor series for sine at 0, and we will see that 0 is not the best place, but that's the question now. So the Taylor series for sine at x0, we already did the work, so this is the expansion, and now we need to use sine with value of x 1.234567, so we just plug it simply. So sine at this point here is equal to this series. Okay, so now we know that this is an alternating series, and we need to find that our approximation is accurate to 10 to power minus 11. So since this is an alternating series, whenever we stop, the estimate of the error is the next neglected term. So that's the result we can use. Or we can use Taylor inequality, it doesn't matter. So whenever you have an alternating series, you have two options. Either you use the alternating series estimate, which is the next neglected term in absolute value, or you use the Taylor inequality. It's up to you, it doesn't matter. So we have this expression here. So this is a general expression of every term. So if we try to use the estimate by the alternating series, which is much easier here, so we need to have this expression smaller than 10 to power minus 11. And in this case, we need to proceed by trial and error. There is no much choice, so we need to shoot values of k in here until this expression, the value here, is smaller than 10 to power minus 11. Obviously we don't exaggerate, we don't go to k equal 10,000, that would be not wise. So we try to find k the smallest possible that will satisfy this constraint. So this is by trial and error, so you shoot some numbers in for k and you try. So after some work, we found that k equal 8 will work just fine. K equals 7 would not. So our best value for k is 8. So if I plug k equal 8, my error will be smaller than this. Good. So what does it mean? Well, if I approximate the expression here, the value using the Taylor series, well, I need to use the polynomial with k equal up to 7, because the next guy with 8 is used for the error. So we need to add the first terms from k equals 0 to k equals 7. So you see now why you don't want to have k 10,000, because you would work for a while to find the value. So we need the smallest value of k that satisfies the error. So in this case that was 7, so we need to add all of these pieces, and then we got an approximation that is correct to 10 to power minus 11. So we needed k equal 7. We said that since our goal was to approximate sine at the point 1.234567, so in radian, using a Taylor series expansion at 0 was not the smartest choice. Another, let's say, better choice would be to use an expansion at pi over 2, because we already computed that at some point. Another even better choice would be to use expansion at pi over 3, because this value here is approximately 70 degrees, so this is 90 degrees, pi over 3 would be 60 degrees. So basically we tried this which is much better than expansion at 0. But if we wanted something even better than pi over 2, we could use expansion at pi over 3. And this is just to show the impact of a better choice of the center of the series, which is closer to the point where we are interested to evaluate the function sine. It's important to be in the neighborhood of this value. So if we use expansion at pi over 2, which was done already at some point, we have this Taylor series here centered at pi over 2. Now we want to evaluate it at x equal 1.23457. We just plug x here, the value, so we get the series. So this series is equal to this value here. Obviously we are not going to use all of it. We need to find an approximation using Taylor polynomial of certain degree, and still the error needs to be smaller than 10 to the power minus 11. So again, what do you do? Well, we have an expression here. So whenever we stop at certain k, this is an alternating series, the value will be, the estimate for the error will be the next neglected term. So basically, this is what we have as an estimate. This is just an alternate expression. So we need to find by trial and error n for which this expression is smaller than 10 to the power minus 11. So in this case, after some work, we found that n needs to be 4. In the previous example, it needed to be 7. So pi over 2 is closer to this value than 0, obviously. So when we used Maclaurin series, so expanded at 0, we needed 7 terms. So polynomial with 7 terms. And then now here, when we are closer with pi over 2, we are closer to this value. The expansion needed only 4 terms. So that's a huge reduction in computational requirements. So it's much faster to compute this to get the same precision. So with k equal 4, so we add the polynomial. So here 2 times k, that's the formula. So with k equal 4, we'll go to power 8. It's not a big deal. So basically, in this case, we get the same precision, same accuracy, but with less terms. Previously we needed from 0 to 7, now we need from 0 to 4. So there is a reduction in computational cost just because we expanded the series at pi over 2, which is much closer to the point of interest. So that's something important to realize. We already suspected that, but we need to just remind ourselves that whenever we need to find an approximation somewhere, it's wiser to have an expansion by Taylor series somewhere close to be in the neighborhood of the point of interest. Another way to apply the Taylor polynomials is to compute some limits. So here we need to compute a limit of this expression, and obviously things are set up in a way that everything works out nicely. So here the limit is when x goes to 0, right? So our goal is obviously to expand sine close to 0 because x goes to 0, so it's better to use Maclaurin series. And then we know the expansion of sine at 0. We remember the formula. Now x cubed here, it's not x, so what we are going to do? Well, we are going to replace x by x cubed, simply, like we do normally. So we substitute x by x cubed in Maclaurin series. So instead of x, I have x cubed. So I get this expression here. So sine cube is equal to this series. Now the next step is to combine everything. So sine cube minus x cube. So this is our series minus x cube. So the x cube and x cube cancel. So we are left with negative x to the power 9 over 3 factorial plus x to the power 15 over 5 factorial, etc. And then we divide by x9. Obviously, you see x9, x9. So everything is set up in a way that things work smoothly. So we have simplification here. So our expression, the complicated expression, is equal to another series. Now if I take the limit when x goes to 0, I take the limit of the series also. When all of these terms have x in them, so there will be 0. So the only term that will survive is negative 1 over 3 factorial. So the limit will be a fixed number, negative 1 over 6. And again, this is just an application where everything works smoothly because the expression is set up that way. So here what we needed is to remember the expansion of the sign in Taylor series, and we needed expansion around 0 because the limit was when x goes to 0. So we need to be careful about that. And then we replaced x by x cubed to have the proper expansion, the proper series for x cubed. Another application would be to compute the integrals, definite integrals. So here the task is to compute a definite integral of cosine x squared between negative 1 and 1, and the goal is to use the Taylor polynomial of degree 8. That is the task that is asked from us in the question. They tell us already that polynomial needs to be of degree 8. So again, the integral is between negative 1 and 1, so we can say an expansion around 0 would be smart because it's in the middle of the interval. So we use Maclaurin series for a cosine, which we remember, and then we will replace x by x squared in this expression, obviously. So we replace x by x squared, we get another series for cosine x squared. Now the task was to use the Taylor polynomial degree 8. So we cut here because this is the polynomial degree 8 for cosine squared. Okay, cool. So approximation of cosine squared by the polynomial degree 8 as asked is given here. So now we are going to integrate. That's the last step. So we integrate the cosine x squared between negative 1 and 1, and it's given, the approximation is just the integral of our polynomial degree 8 between minus 1 and 1, obviously. So we integrate the polynomial as we usually do. We evaluated the bounds and we get approximate value of the integral. So that's another application. Obviously, if the question was to use a polynomial degree 12, well, we will use another term, etc. So depending on the question. This is a curious one also, similar to the previous question. We need to use polynomial degree 5 here, and the function is sine x over x in the interval negative 1, 1. So again, we would use expansion of sine around 0, so Maclaurin series. Now it's curious to realize that sine x over x, well, at 0 we have potentially a problem, but we remember that the limit when x goes to 0 of sine x over x is 1, so we don't have actually a problem. It just looks like we have one, but we don't have a problem. So what we are going to do, well, we are going to simply realize that we are integrating in the interval negative 1, 1, so it's reasonable to use Maclaurin series expansion because it's centered at 0. So we have expansion of the sine, we produce it, and here the question was to use polynomial of degree 5. So we use the polynomial degree 5 for sine, and then next step, we divide by x, the entire expression here, so we get the simplified version. And now the last step is to integrate between negative 1 and 1, so approximation of the integral is given by the integral of this polynomial, sin x over x is approximated by this polynomial, so we integrate the polynomial normally, and we evaluated the bounds as we normally do, and we get an approximation for the integral. So those are some of the applications of these Taylor polynomials. So we can use them to approximate the value of different integrals, definite integrals, some limits. We can estimate the error using Taylor inequality to estimate the error, or sometimes if we have an alternating series, we can use the absolute value of the next term as an approximation for the error. So those are pretty much applications for the Taylor polynomials, and it's important to try to solve some of these problems just to be comfortable. And obviously you see now the importance of memorizing a couple of these Taylor expansions for some functions that come regularly, so that's why we have those tables at the beginning. I hope you will try to solve some problems to practice this quite easy material, but requires some practice just to be comfortable in applying all the steps.